Welcome back. Today we are continuing our study of numerical integration. We will focus on how to handle sampled data, explore stochastic methods, and discuss how to diagnose the accuracy and physical meaning of our results. By the end of this session, you should be able to integrate discrete datasets using the trapezoidal rule and understand the shift from analytical functions to measured data. We will also implement Monte Carlo integration and learn how to interpret numerical results through convergence and physical reasoning. Let us briefly recap what we covered in Part 1. We defined the integral as an accumulation of contributions over an interval, representing quantities like work or displacement. We also saw that the SciPy quad function provides both an estimate and an error bound, but we must always validate these results ourselves. To get started, we need our standard scientific Python toolkit. We are importing NumPy for numerical operations and matplotlib for visualization. Specifically, we will use trapezoid and cumulative trapezoid from SciPy's integrate module to handle our sampled data. We have also initialized a random number generator with a fixed seed. This ensures that the stochastic results we generate later in the lecture are reproducible and consistent for everyone following along. In real-world physics, we rarely have a smooth analytical formula for a function. Instead, we often work with discrete values, such as velocity measured at specific time intervals. To find the displacement, we approximate the integral of velocity over time using the trapezoidal rule. Here, we generate synthetic velocity data that includes a bit of measurement noise. We then use the trapezoid function to calculate the total displacement over the 20-second interval and use the cumulative version to see how that displacement evolves at each step. The final part of this code sets up our plots. We want to visualize both the raw velocity measurements we started with and the resulting cumulative displacement curve we obtained through integration. The console output tells us that our estimated total displacement is approximately 47.96 meters. This single number gives us the total change in position, but the plots will show us the full story. Our first plot shows the sampled velocity data points connected by lines. Notice the fluctuations caused by the simulated noise we added. This represents the kind of messy data you would expect from an actual sensor or experiment. By integrating that noisy velocity data, we get this cumulative displacement curve. Even though the velocity was fluctuating, the integration process smooths those variations out, showing a steady overall increase in the particle's position over time. It is vital to remember that when integrating sampled data, your accuracy depends on the quality of your measurements and the spacing between points. The numerical method itself might be perfect, but if you have missed key features between samples or have too much noise, your physical interpretation could still be wrong. Now let us move to stochastic, or Monte Carlo, integration. Unlike deterministic rules, this method uses random sampling to estimate an area. By counting what fraction of random points falls under a curve within a known bounding box, we can approximate the integral. We implement this by defining a function that draws random x and y coordinates within a specified rectangle. We use a Boolean mask to determine which points lie below the target function and calculate the mean of that mask to find the successful fraction. Multiplying that fraction by the area of the bounding rectangle gives us our final estimate. In this example, we are estimating the area under a sine wave from 0 to pi, and then comparing that result to the precise value provided by the quad function. The results show that about 63.7% of our points fell under the curve. When scaled by the rectangle's area, we get a Monte Carlo estimate very close to the exact analytical value of 2.0. Visualization is key to understanding this. We are plotting the sine function and a subset of our random points. You can see how the points are scattered throughout the rectangle, with only the colored ones contributing to our area count. This scatter plot illustrates the hit-or-miss nature of the algorithm. The estimated area is essentially the probability of a random point landing in the shaded region, which becomes more accurate as we increase the number of trials. Because Monte Carlo integration relies on randomness, the estimate will fluctuate. To see how it converges, we will test a range of sample sizes, from 100 points up to 30,000, using a consistent random seed for each test. For each sample size, we calculate the absolute error by comparing our stochastic estimate to the true value. We will then plot these estimates on a logarithmic scale to see if they trend toward the correct value as n-p increases. Finally, we will generate a log-log plot of the absolute error. This is a standard way to visualize convergence in computational physics, helping us see how quickly the error decreases as we throw more computational resources at the problem. Looking at the printed output, you can see that with only 300 points, our error was quite large at over 10%. However, by the time we reach 10,000 points, our error has dropped significantly to less than 1%. The convergence plot shows the estimates bouncing around the true value of 2.0. While the trend is generally toward the exact value, notice that it is not a perfectly smooth descent. Because it is random, a larger sample can occasionally produce a slightly worse estimate by chance. This log-log plot of the error makes the trend clearer. On average, the error decreases as the square root of the number of points. To get one more decimal place of precision, we typically need to increase our sample size by a factor of 100. Let us look at a common scientific application: finding probability from a density function. For a standard normal distribution, we calculate the probability of a value falling between -1 and 1 by integrating the probability density function over that range. We define the normal probability density function and then use the quad solver to find the precise area between our limits. We will also generate a plot to visualize this 1 sigma region under the bell curve. The code then shades the region between -1 and 1. This visualization helps confirm that we are integrating the correct part of the distribution before we trust the numerical value. The resulting plot shows the classic bell curve. The shaded area represents the probability we are calculating, which should be about 68.3% based on standard statistical theory. The quad output confirms this, giving us a value of 0.682689 with an extremely small numerical error. This high precision is expected because the normal distribution is a well-behaved, smooth function. Now, let us try to get the same result using the Monte Carlo method. We define a bounding rectangle that just barely encloses the peak of our distribution within the limits of -1 to 1, and then we run our random sampling. With 20,000 random points, we get an estimate of 0.68287. This is within 0.00018 of the quad result, demonstrating that stochastic methods are quite capable of providing accurate results for statistical problems. As we move toward more complex problems, always use these diagnostics. Check your limits, look at the integrand's shape, and verify your units. Most importantly, always check for convergence by increasing your resolution to see if the result stabilizes. Let us demonstrate deterministic convergence using the trapezoidal rule on a Gaussian-like function. We will vary the number of subintervals from 10 up to 640 and track how the absolute error relative to the quad result changes. We will plot this error on a log-log scale. For the trapezoidal rule, we expect a very specific relationship between the number of intervals and the accuracy of the result. The numerical output shows the error dropping rapidly. Every time we double the number of intervals, the error decreases by roughly a factor of 4. This tells us the trapezoidal rule has second-order accuracy. This linear trend on the log-log plot confirms that predictable convergence. Unlike the stochastic method, which was noisy, the trapezoidal rule improves in a very structured, smooth way as we increase the number of intervals. Be wary of these common mistakes. Never confuse a single function value with an integral, and always be mindful of your integration limits. Swapping the limits will flip the sign of your result, which can lead to major errors in physical models. Also remember that quad returns two values, the estimate and the error. In Monte Carlo integration, the most common error is forgetting to multiply the fraction count over NNP by the area of your bounding rectangle. Now it is your turn for some guided practice. Try integrating the exponential of negative x squared from 0 to 1 using both quad and Monte Carlo. This will help you get a feel for setting up the bounding boxes correctly. In this practice code, we set up 10,000 random points. Pay close attention to how we define the practice ymax. If you set this too low, you will clip the function and get an incorrect, non-physical result. We will print out both results and the absolute difference between them. This is the same workflow you should use whenever you are testing a new numerical model. The results from the practice show excellent agreement. The difference is only about 0.0007, which is quite good for a stochastic estimate with 10,000 points. To summarize, we have seen that numerical integration is a powerful tool for accumulation problems where analytical solutions are not possible. Choose quad for smooth functions, trapezoidal for sampled data, and Monte Carlo for probabilistic area estimation. Always validate your results with plots and convergence tests.